Well, welcome everybody. We have the sneak peeks that we're doing this fall for those who have heard about the modeling instruction workshops and have been curious, but would like to just have a little bit more heads up on what it's about so that you can decide, hopefully, that it's valuable enough for you to invest the time. All of us know how much of an investment it is, because we've all, Brooke, me, Larry and some others have all been through the workshop experience and invested in at least 2 weeks or longer to be trained in modeling instruction. And so we're going to give you a little taste of what it's like as well as we can in an online setting.
Yeah, Brenda's going to get us going with a little bit of an introduction. And for those who are just joining, I've done this a few times now already, but I'm dropping a link in the chat for a little bit of technology that you're going to want to have downloaded to use during our breakout rooms. So if you haven't had a chance to download that yet, go ahead and get it real quick. And then, yeah, let's go back to Brenda.
Okay, move things around so I can get to what I need. Okay, so um, we, Brooke, you're going to need to monitor the chat because I'm
I got
not
it.
going to
Don't
be able to
worry.
get to it.
Yeah, I got you.
So I'm Brenda Royce. I've been working with modeling instruction since first training in 1998 and used it in my classroom beginning that fall. Been involved in helping write curriculum with Larry, who's with us, and Brooke, you want to introduce yourself?
Yeah, I'm a newbie. I've only I started with modeling in 2014. I was lucky enough to actually start at my place of work where they were already using modeling, and so I just got trained up with it, and then I got to take a modeling workshop and just saw the value in it. It was great. So I've kind of stuck around, and now I have been working at just I got involved with some of the leadership of this and kind of helping to move the organization forward, and I've been really grateful to be a part of it. That's kind of how I got roped into helping out today, and I've been very grateful to be able to work with Brenda, so here I am.
Okay, and I didn't mention Brooke's coming from I think a little bit of high school college experience, and I have high school experience
Yeah.
teaching high school chemistry. And there it goes. So we're going to just really fast because the whole point of this is that modeling instruction is a way of teaching, but just so that you kind of know what we're dealing with, we're talking about a student-centered approach, that we guide students learning dialogically, not, there's very little lecture usually. So it's more in conversation, develop conceptual models. We'll go over a little bit more about that, about core ideas of science, and help students apply their models to new situations, with a curriculum that's structured around a sequence of models following a story rather than a sequence of topics. And so you'll get to see here. So modeling instruction, what's a model? This is our classic view of a model is really, we consider a mental model. And when we look at a physical system, we get an idea, we do testing and so forth, and we develop an understanding of what's going on, which is our conceptual mental model. But then we have to communicate back and forth as well as represent what we've seen so that we can develop that understanding through verbal, graphical, algebraic, mathematical, diagrammatic methods, in order to capture the features of the physical system that we had. A couple of years ago, we had Dr. Cynthia Passmore from UC Davis share with us on another slightly different view of a model where it's a way of bridging between phenomena and questions, and both are quite compatible with what the teaching is. One is really what is a model, the other is what is a model for, how is it useful? So the point is models are useful and they represent something physical. So in our teaching pattern, we develop models, help guide students to develop a model. You'll notice, those of you familiar with NGSS, that all of the science and engineering practices over here are just deeply embedded in what we're doing. And after developing it, then we deploy or use the model by testing it, asking more questions. What does this model help us predict? Arguing from the evidence that we see from labs and experiences we're having. And in the process, refine the model until we hit a point where, oh, the model fails. And then we ask a new question, develop either a new model or a heavily refined model, and start the process over again. So this is just a kind of visual what some of the things might look like in a classroom, with investigating, analyzing, representing, and then discussing and refining ideas together. So move from experience to the various representations, verbally describing things, then moving to the symbolic as the last item that we really deal with. Is the most symbolic parts come after the development of the understanding. So we are going to basically walk you through an experience with what would be our unit 2 in modeling chemistry, dealing with gas behavior. This is selected in part because we have the videos necessary to do this in an online setting. But in a modeling workshop, we would put you in student mode. You would be actually participating as the student and trying your very best to kind of shed yourself of your expert knowledge so that you can see the curriculum through the lens of the student. Through the lens of the student. It's amazing the things that I have learned having to take that role about what my students are experiencing. And then you would walk through the actual labs and demos and activities that would be part of the particular content area, say chemistry. So in this particular unit, we would have some things that we've already done, but one of the things that's real core to what we want to talk about is have students blow up a bag with a student laying on it and explore what gases are capable of doing. And then turn around and explain, how does this happen? Can you use our idea of the little particles that we've been talking about that move around, and explain how a person's body got lifted off the table? Another possible activity is exploring how much a gas pushes back inside of a container like a balloon, and relating that to area. And then they have to explain, why do we see this connection between the amount of area that we came in contact with and the force that we measured? Which just kind of gets kids really thinking about what gases are doing. And then we can go and experiment. So Brooke has some materials that we might use as we consider, how could we vary the pressure of a gas? We have a container. So Brooke, share with us some possible containers we might use to keep a gas in. You're muted.
Do you want to stop sharing for just a minute? So I'm a little bit, I know. Can we just focus on me for a minute? I'm just like, yeah. You want to click on, so you can see a little bit better. So what I have in front of me is a little container that would be maybe handed to you as a student, that you would have as some materials that you would have to work with. In my little container, I have some items that you could use to explore gases. One of these is, I have a little Erlenmeyer flask. It's about 125 milliliter flask. I also have a stopper that's got some, lock things. You've got some tubes in here that we can connect this to. I've got a gas pressure sensor that this is going to connect to. I've got some tubes, these connect. I've also got this, I've got a syringe that will open. Oh, it's a little stuck right there. Let me get that going. So it opens, it closes. I've got one of those. I've got a temperature probe that we can do into, like a gas sample. I got all this stuff inside my kit. So these are the items. So with that information, we go back to sharing.
What's something that you could do? You have an option of a flask, you have a syringe, but what are some things that could be varied when we know that these little particles in the gas phase are just moving around? And we have
One
someone
suggestion in the
saying
chat was
heat
to
it
heat
up.
it up,
Okay,
squeeze
heat
it.
it up. One, use the screen, add more gas to a container. Any other ideas?
So push more gas in and put it on ice.
Okay, so we could heat it up or put it on ice. Add gas or remove it.
Okay, love it. Any other ideas we want to throw out there? You feeling pretty good about that?
So compressing, changing the volume. Is squeeze it meaning changing the volume as well, I presume?
I guess that's what I was thinking, but maybe I'm
Okay.
misunderstanding that previous one.
So if there's any clarification.
Yeah,
So I'm
I can just
seeing,
add that. Compress a chemical reaction. Yeah, do we know about those yet? I don't know if we know about.
actually, in this particular context, we don't have that yet. I didn't give that context.
Yeah.
This is
And that's one of those
unit
tricky
2,
things.
very
Yeah.
early in the curriculum, where students are not even processing whether there are molecules that exist, just simply particles.
Yeah.
Just little small little things that move around.
And I understand, like, we are trying to like invite you to kind of jump in mid-curriculum. Like, here's what we know so far. We like the story, and we are asking you to jump in. So yeah, at this point, unfortunately, students don't even know that, as Brenda was explaining. So
if we were to look at this very simply, we have now heating it up or putting it on ice. What would we be varying about the gas if we did that? What could we measure to know whether that changed? Okay, so Catherine says temperature would be one thing that we could vary. Okay, if we were to squeeze it or compress it, what would we be varying that we could measure? And we have volume. Okay, so we're suggesting right now that changing the temperature or the volume might affect the pressure. And then we have adding or removing gas, which would be, as one of our participants has said, the amount of gas. Okay. Are there any other thoughts on what we could do with a container of gas that would change the pressure of the gas inside that container? Okay, we have a suggestion of changing the outside pressure. My students always say, let's take it, up in elevation. Okay. Well, but would that vary what's going on inside the gas, inside the container?
it's a great question in the chat.
Yes, Tufik, I hope I'm saying correctly. Yes, they have the balloon is, we have had a conversation about air pressure and measuring pressure as a amount of force on the inside of the container or on a surface. So yes. Okay. So we have basically three things that you have suggested that we could measure. We could measure temperature and see how it affects pressure. We could measure the volume of gas and see how it affects pressure. And we could measure the amount of gas. And in our model of matter as made of tiny particles, Najdi, thank you. The amount of gas would mean we would be putting in or taking out the matter particles themselves. So as we explore this, then we need to come up with how can we go about changing the volume of those. When looking at changing the volume, what container would you use of the ones that Brooke presented? Okay, Catherine is suggesting a syringe. All right. And what would we use for a container if we wanted to vary the amount of gas? Now, that one might not be so intuitive. Which one, where we know how much we are varying it by, would a flask or syringe give us a better way of understanding how much gas we have present? Okay, Carla's suggesting the syringe would. All right, so if we did that, we can open and close the syringe, but there has to be a certain condition. As we're doing these, we have all these variables that we want to be checking on, and we can only allow one at a time to change. So with the volume changing, we can do that with a syringe, but there's a really important thing that we're going to have to keep constant. That would be the amount of gas and the temperature, which means our syringe has to remain sealed. Fortunately, putting it on a pressure sensor keeps it very nicely sealed. So we could vary the gas of a closed syringe. But the amount of gas, if we want to vary that, that would have to mean we would have to be able to keep the volume constant while we're also taking gas in or out of our container. And we'll look at that in just a moment, but we'll have to keep the temperature constant, which, as my students say, keep your hot hands off of it. So in measuring the temperature, that one is going to also mean we're going to have to keep the volume constant while we're making it very hot and very cold. Okay, Catherine suggested a flask with marking stopper. Can you explain what you use your voice and explain what you are talking about there?
Hi there. Sorry, I think I was talking to amount of gas when I was saying the flask with the stopper. You could maybe try and figure out something with the amount of gas utilizing that stopper with the tubing, because you wouldn't be
Okay,
altering the volume of the container. You could
yeah.
remove and take out amount. And then also, since it had the temperature probe, you could maintain volume while altering the temperature.
Okay, for changing temperature using the flask is what you're suggesting, Catherine?
Yes, correct.
Okay, yes, we could. We could keep that sealed up and constant, and and we would know that the volume would not change. But then we can change the volume. We have an interesting dilemma, though. How would we go about changing the temperature of the gas in a way that we know what that temperature is? Can you think of how you might vary? You have this nice closed system, so no gas gets out. How are you going to change its volume? I mean, its temperature, so that you know what the temperature is and can measure it. I have a container of water to be heated and cooled. Okay, and where's your gas going to be? Place the flask in the container of water. Okay, we could do that. And unfortunately, we can't stick the temperature probe inside the stoppered flask or we would break the seal. So, but students, as we know from some earlier experiences, if we put two things in contact with one another, they will eventually reach the same temperature. Okay, so what if we put the flask in the water and put the temperature probe in the water and just give it a few minutes for everything to stabilize? They should come to a place of reaching the same temperature in a fairly short order. And then, so that one goes pretty well. We can change up what the temperature is. The volume is pretty easy. Amount of gas now. We want to be able to know exactly how much we have. Brooke, can you hold up a syringe? And you're sharing right now, right? Okay. All right. So if we have our sealed syringe and we measure the pressure inside of it, we would need to add, say we want to add some more gas. So we'd have to take it off our temperature, take it off the pressure probe. Just put the flask down. We're talking about this. Do you have a pressure probe? And just attach it. Okay, so we've measured the pressure of that gas and we want to vary the amount of gas. So if you pull, we're going to have to pull the syringe back off. And let's say we add some more gas. Brooke, what volume did you have on that gas first?
It was at 12 milliliters.
Okay, so now then you add some more gas.
Now it's at 15.
Okay, and we put it back on there, but our volume has changed. So now
Yeah, it's different now.
we would need to return it to the volume that we had. And then hold on tight. So if we can take it back to 12,
Yep.
then we would have a constant volume, a constant temperature, and a change in number of particles. So what we're going to do is have you carry out the experiments by watching some videos. We've had one person asking if we can share the folder again, please.
See, we want the gas lab behaviors, and we want this one share. Copy link. I'm going to drop that in the chat real fast for us. Don't you worry, I got this. And paste. Enter. There we go. So that's the link. Well, that's directly to the slides. Is that what we want? Do we want the whole folder? I was doing the slides specifically.
Oh, well, they need
They're going to need their group numbers and their assignments first.
yeah. Okay. We're going to put you in some breakout rooms. We have 6, which means we have 3 experiments and 2 groups are going to work on each experiment. There's a set of videos in a folder that Brooke has shared. Okay. And a set of slides there. You need to, Brooke, what's the name of that?
On the link that I shared, there's a set of slides. On the slide that you go to, there's a link to the video for your group.
Yeah.
Yeah.
And there's just a video that shows the experiment being carried out in a way that you can collect the data. We're going to ask you to open up graphical analysis, at least one person in your group. Well, I'm going to open up 6 breakout rooms, and you're going to go to the slide that corresponds with your breakout room. So you're going to have 2 or 3 people in each of your rooms. Would you, on your slide, you're going to be asked to show your graph. And at the end of the slides, there is a tutorial on how to do the basic that you need to enter data on in graphical analysis. So the rooms are open, and Brooke and I will be jumping in where we can and between the groups to help you out. We'll give you about 15 minutes to collect the data, or a little bit less. Please go to the slide number that corresponds with your group number. So group 1 should be on slide 1, group 2 should be on slide 2, and group 3, etc. It'll tell you which experiment you're working on.
All right, I think everyone's back, Brenda, if you want to get us rolling.
Okay, so we have, at this point in a workshop, and we are going to kind of jump over some of the steps because of time, we would be looking at what just some whiteboards that are, of good presentation size, where students would have collected up their lab data much like you did on a slide. And we can now start to look at comparisons of the data. So, group 2, can you describe what you were doing with your particle diagrams and how that relates to your graph?
Can you hear me?
Yes.
Hi there. This is Rob. Chris and I did pressure versus number of particles. So we watched the video and plotted the points. And as you can see, the relationship is fairly linear, actually really linear. And what we discovered is that for equal additional amounts of gas, the pressure went up by a regular amount. So we tried to make our particle diagrams with increasing the same number of particles each time. So we made 2 our unit in the particle diagrams. The whooshies are a little hard. I wanted to try to move them in different directions, but
I know.
it was limiting because anytime I tried to turn it, I changed their length, which of course would mean that we sort of had different temperatures, maybe, I don't know, but anyway, it worked. It worked well, and
Okay.
I've lost track of what else I'm supposed to say here. Maybe Chris can fill us in.
I think that was good.
All right.
So if you went from 2 to 4 to 6 little particles here in the same
Right.
volume, what happened to the pressure when you went from 2 to 4 to 6?
That actually I don't know that I looked at that. We were just going up by like milliliter at a time. So I'd have to go back to the data, but I would guess that it was doubling and quadrupling there.
Okay. Okay, so all right. And then we also had pressure versus number of particles. So Brooke, if you pick one of those. Oh, we have pressure versus volume. Okay, group 4, can you explain why you see the pressure dropping from a particle perspective?
I'm sorry, from a particle?
Yeah. We can see in your graph that the bigger the volume, the less pressure you had.
Right, from a volume, not a.
I don't know what I may have said something.
Sorry, yes, from a
Sometimes the
volume.
brain and the
yeah.
tongue get separated from one another.
Yeah, so we were noticing that it was inversely related. So as we decreased our volume, our pressure was increasing.
So if you just picked a couple points and looked at if you took your volume to double the volume that you had previously, what's happening to the pressure?
The pressure is decreasing. Is that what you're asking?
But I specifically said doubling. Is there something you can say that's more
Quantitative.
exact, quantitative, for when the volume doubles, like from 10 to 20, 8 to 16?
Looks like it's about half.
About half?
Yeah.
Okay, so if we double the volume that holds the gas, the pressure goes down by about half.
Correct.
Okay. And with the number of particles, if you double the number of particles, the pressure appeared to double. So we have some really comfortable little proportions here that would be easy to work with. And if we look now at our one temperature graph. Okay. Group 3, what do you see here in terms of the trend with the pressure and temperature?
We noticed that as the temperature went up, so did the pressure. And as the temperature went down, so did the pressure.
Okay, and what's happening to particles as they get colder or hotter at
When
the
they
particle level? Huh?
And when they get hotter, they move faster. And when they get colder, they move slower. We couldn't really get our whooshies in there. We didn't have enough time.
Yeah, I know. Slides and online is hard. And what were you trying to say with your particle diagrams to explain why the pressure is different?
Because my particles are more spread out and moving faster, they can hit the sides, like the side of the container more. So we're going to have more pressure.
And you said they're spread out more. So was the volume changing?
The volume of the container is the same, but the particles inside are moving and spreading around, moving faster.
So if I make them cold, do they cluster somewhere in the flask?
Well, they move slower.
They move slower.
Right.
Okay, how would that affect that hit on the side of the container if they're moving slower or faster?
Physics brain or chemistry brain?
Student brain.
Student brain? Well, it's going to push less, so it's going to make it less pressure. It's moving slower.
It's moving slower, okay, because we would certainly prefer being hit by me throwing a softball at you than a professional pitcher hitting you with a baseball and a fastball.
Right.
Considerable more force. Okay. All right. So, but we have an interesting phenomena here. What if you take your temperature from like about 20 to about 40 degrees Celsius? What happens to the pressure? Does it also double like those other nice ones, either doubled or cut in half?
It's kind of hard to see there. I would say it looks like it's increasing at the same rate-ish.
Okay, so we've got a nice linear relationship. But
Right.
what about doubling? If you double it, like the number of particles doubled, that's kind of a nice one. Does this do the same nice doubling?
Well, I go from 20 degrees to 40 degrees. I go from, yeah, I should actually just.
So the temperature goes. It is hard to read your axis on the slide. But we notice, though, that when the temperature is 0, we're able to get it colder than that. And are the particles still moving at this lowest temperature particle?
I would think they're
We'll
still
come back.
moving.
And what's your evidence?
Well, because there's still pressure, so they have to be hitting the container.
Okay. We have a nice linear relationship like the number of particles does, but we don't see signs of doubling because we don't even have 0 pressure on our graph.
Right. And we notice that when we go from 20 to 40 degrees, I'm only going up like from 93 to 97 degrees.
That's not much
So
at
that's
all.
not doubling.
But if we could figure out what temperature the pressure goes to 0.
That's what we were doing when you came in. That's what we're trying to figure out.
Well, we can actually, graphical analysis does a nice job of letting us do that. And we would do this with the students and have them put a good linear fit through their data and then extrapolate back to where the pressure drops to 0. I'll just tell you in the teacher discussion mode, yeah, it's wobbly because it's student data. This is very good controlled teacher generated data that you have here. But I typically, with students getting some, if they have a good linear fit, usually they get values for the temperature when the pressure drops to 0 of about -250 to about 400, which at least puts us somewhere kind of in the ballpark with leaks and all the other things that inevitably happen, where we can redefine and work back with a Kelvin scale to get it back to a linear proportional relationship where the pressure and the temperature are 0 simultaneously. And we have a discussion about the need to get it into a different scale because Celsius isn't actually related to particle behavior in the same way that Kelvin would be.
Yeah.
So
we got actually -351 if my memory is correct.
Excellent.
Yeah.
Okay, so where do we go from here? We would be working with students.
Oh, sorry, we're gonna go back to this one.
Brooke, I think we're quite off script at this point. But how can we use the patterns we've observed and our explanations in order for us to be able to look at a gas situation and make some predictions about what's going on? This is where we're going. This is where we get into deploying the model. So going on to the next slide, we have created a model of understanding gases as these little particles in motion that collide with the containers that they're in, the sides of them, producing a force on the side that we measure as pressure. We've seen when the volume versus pressure versus volume, that if we double the volume, the pressure cut in half. And we can see by increasing the volume, we have the gas able to interact with much bigger areas of the surface of the container. We would have students articulate that with number of particles, that if we doubled the number of particles, we're able to double the pressure. And we can see as more particles get in there that there are going to be more forceful interactions with the side of the container as more particles are able to collide. Temperature, when we get it into the Kelvin scale, we see that as the temperature goes up, the particles are moving faster and faster and faster. And those faster particles put more forceful collisions onto the side of the container, increasing the pressure. And we would have looked carefully to see that, oh yeah, you can double the Kelvin temperature and then the pressure will double. So Brooke, why don't you
So
just—
one of the things that's hard about gas laws, I know we're out of time, so I'll just do this really quickly to kind of show you one of the things.
We just want to leave room for questions. That's why
Yeah.
we're kind of pushing here.
Is that we can organize all of this and help students basically use the knowledge that they have just generated themselves to be able to predict the gas laws without ever actually memorizing an equation, which is one of my absolute favorite. When I first learned this, it's my absolute favorite thing. So here's an example. Let's imagine that we have an initial pressure of, let's say, I've got initial pressure of 100, turn my pen on, here we go. There we go. It's got about 1 atmosphere, 1 atmosphere. Let me make that a little bit fatter so we can read it easier. There we go. 1.25 atmospheres, okay? And let's say it's in a container that is 125 milliliters, okay? And let's say that container, you know, if one of these containers got a piston type thing, you can open it up, make it bigger, and that's going to go to 175 milliliters, okay? So I can use this chart to help my students organize that information. That's one of the challenges with the gas laws, is just organizing the information that I have. Now in this, I'm given, and basically the question is, what will the new pressure be? So I can identify here, okay, my final pressure is the thing that I'm looking for. I know that the temperature is not changing, so I'm gonna go ahead and just draw a line through that. And by the way, this is how I use the chart. There are some variations with how different people end up using the chart. Just nod out to everyone. I also know that the amount of gas is not changing, so I'm also gonna draw a line through that column. Okay, so then I'm gonna say, well, what is happening to the volume? The volume is going up. The volume is increasing. Well, from the experiment that I just conducted, right, I can look back at my data and say, well, when the volume goes down, I know that my pressure is going to go up.
You just switched them.
I was like, sorry, I did that backwards. I'm sorry. Undo. The volume goes up, the pressure needs to go down. I said it, there we go. Thank you. So, thank you. Yes, my pressure is going to go down. So I know that's going to be the case. So for my ratio, I know that that needs to be less than 1. Right, so what I know, and I'm not joking, I call this and I know that people do, it's the uppy downy technique, which if it needs to get bigger, make it get bigger. If needs to get smaller, make it get smaller. You never need an equation. So this is what this looks like. I take my 1.25 atmospheres. I am going to set up my proportional ratio so that it is less than 1. And if it's less than 1, that means little number goes on top. Little number goes on top. So I look at my 2 options. These are my options. My little number goes on top. My 125 milliliters. My 175 milliliters. I, into my calculator, do my number, and that comes out to be 0.89, and then it has like a 2 whatever. Look at it, round it to your appropriate number of significant figures. That comes out to a 3 right there if you round it appropriately, atmospheres. And then we can use it to solve. So in the folder that we shared, there is a whole other slide of slide deck of, we were going to give you the option to go through and do these. Those same sort of problems were on a worksheet that you could use with students in the future if you wanted to. But we won't have time to do all of that. We do want to leave some time for questions, but this is an option of how you can use the experience that they now own for themselves to apply now to doing the problems, rather than just saying, here's some gas laws, learn them, memorize them, and, regurgitate them. Now they own that experience, and now they can predict them, which is one of my absolute favorite things about this whole modeling cycle, is that they own that information. They've experienced that information. So this is part of the reason of modeling.
Yeah, but when we were getting ready, Brooke and I both commented that occasionally students say, but you said, and we said, when did we ever say that? We didn't say that. You said it.
That,
you did the lab, you said it. So now, because we have 3 different proportional relationships here, we could also change the temperature, and we would just add on another proportional change. If we could change the number of particles, we could do the same thing. We can use some understanding of just particle behavior and say, well, if we increase the temperature, what would happen to volume? And I tell my kids, take your balloon from a cold air-conditioned building and put it in your car in Fresno, where I live, in August, and what's going to happen to the volume there. And then they discuss the increasing speed of particles is going to cause that balloon to expand. Oh, okay, so thermal expansion idea, and this gets bigger. And it would be also in a proportional manner that if you doubled Kelvin temperature, the volume doubles. And so on. And they can solve some very complex gas problems and not have a single equation that they have to ask and remember. Test day, they could have whatever we use, we have the analysis table for them to go through and organize their information, analyze it, and be able to answer questions about it. This is just one example of a way that we could deploy or use the model that we created of gases, the pressure, temperature, volume, and number of particles all have proportional relationships between them, either direct relationships or inverse relationships. So, any questions you have about what it might be like to jump into a workshop or the modeling approach, or what the heck just happened? That we can help you with.
And I did just drop the link in the chat for the whole folder, so that you can find the slide deck for what you worked on today, the slides for the practice problems that we didn't get to, for all the videos. They're all in there, so we can share all that information with you. It's all there for you. You betcha. You're welcome. Yeah, any questions for us? Anything we can help you with? It is the last thing we do want you to do. Let me go pop back here. Okay. Just find us. We're everywhere. These are all the handles across all the socials that you can find us. Yeah, across YouTube, Twitter, now X, Instagram, Discord, everything. You can find us there, including a podcast. Yes. And Sue is that voice who was just reminding me to make sure we get out the survey. That's Sue. This is her email. She knows all of the things about all of the workshops that are coming. So if you have questions or want to get more information about that, you can get her email. This is it, to ask her questions about getting registered or getting signed up for those. That's there. But this is the survey that we would love for you to take, just to find out a little bit more about your experience, how we could make this better for you, and yeah, what brought you here today before you go. So you want to grab that while we're chatting. We can answer more questions, of course, but please take a minute to grab that before you go.
I had a question about phenomena. Do you set up the unit with a specific phenomenon, such as the lifting the student one, that ultimately they then explain with
Yes.
these?
Yeah, we always try to start a new concept cycle, a new modeling cycle with some direct experience with the students. Unit 2 happens to have a number of very direct experiences. We actually start the unit with exploring gaseous and liquid diffusions in order to, and then check the difference of when it's cold and hot water that we're diffusing dye in. Kids need to explain what's going on and why we're seeing a difference in rate at which things move through the liquids when it's hot and cold. And that brings us to the idea for the first time that particles absolutely must be in motion, because they have to be colliding with one another in order to spread around. Anyway, yes. So every unit will have experiences directly that we don't tell kids about the idea. We let them experience it first. And what's gorgeous about that is everybody's now has a common conversation point about the ideas, no matter what background they came from. I do not have to hope they understand something. We can go back and say, well, when you saw the hot and, we put the dye in the hot and cold water, or when you were doing your gas lab with the number of particles, or when you, in the previous unit, were looking at how different changes and what happens to their mass, or what, all the things that we do later, looking at a reaction, looking at all these things, everything has been anchored in an actual direct, observable, measurable experience.
Brenda,
Do
can
you
I
then
jump in?
use those in, oh, sorry.
No, keep going.
Well, I was just wondering if you use those then in assessments as well, or if the assessments look more like more traditional problem solving.
It can be, you can do like lab practical type assessments. You can do, it depends. How this content is assessed is entirely up to the teacher. It's not a universal thing. Some people are using mastery style, quizzes. Some people are doing, unit tests. We have lab practicals where you may be given a practical problem. You may be given a project to create. There's just a lot of options. But even if I give when I give paper pencil tests, they have conceptually based questions in them. So this would have them having to explain or diagram or interpret a diagram, or it would not just be here to get, okay, now answer a bunch of quantitative gas problems. It would have a lot of conceptual basis in that test, assessing their understanding and not just their capacity to keep going on doing calculations.
Thanks. Yeah.
There's a lot of resources available that have already been developed for the standard-based grading for those who are interested in that. And I have seen teachers even do journals where the students take that, and then in smaller classes, they sit down and do interviews with the students and say, you know, explain this to me, and see how well they can talk about the phenomenon and to explain the concepts, and that's what their grades are based on. That can be, you know, very involved in. So there's not a lot of people who do that, but I've seen it done. So there's lots of options.
So if I can jump in for a second, Thomas asked a question about phenomena, and I think it's important to recognize that the phenomena that students experience at the onset of a unit is what gives the motivation for doing the labs. It isn't like, hey, we're going to do a set of gas pressure labs. It's how can we understand, we observe some behavior, how can we make sense of the behavior? Well, let's do some labs to see what's going on. What kind of regularity or patterns do we see? We see that the pressure goes down when the volume goes up. How can we account for that? And that's where you have your particle representations. So it's all based on starting off with some phenomena what you're trying to make sense of.
Mhm. Yeah, have you ever heard of the Summit curriculum that was being taught in my district for a while? And my colleague taught Summit and I didn't, but they used this approach for explaining why aluminum can crushes when you invert it into cold water after boiling a little bit of water in it. And so we've been trying this approach with the can crush module is what we call it. And it's been good. It's been less, we have not at the high school level used this quantitatively to the extent that one could, but it has certainly generated more discussion. In our dreams, we would wish for a lot more discussion and a lot more curiosity, but maybe that'll come with time.
Brooke, could you take us back to some of those introductory slides where it showed my students in the classroom?
You betcha. Oh, and that's not the fastest way to do that. Let me do it this way.
There it is. Okay. In this approach, all of you, Thomas included, that we've got these different, these pictures are just examples that are not all from the same lab experience or whatever, but students are actively engaged. You can see them doing this. We use these whiteboards a lot because they reveal student thinking. This is where instead of a slide, they would have been using markers and drawing these, and then we would have gathered in some form, whole class or in groups or something in order to share what we found and discuss its meaning. This group, I happened to have my class in a big circle in the room, and I just zeroed in on a group that was sharing what they had found in their particular part of this.
Which I'm going to interrupt. We affectionately call board meetings.
Board meetings, yes. Where
They
the
call
boards
everybody
meet.
to the board meeting, yes. Which the person is always going to kick out of it. Yeah.
And even if you go on to the next slide, Brooke,
I think you went, yeah.
that you can see the one where the blow-up student, they had to do something to show what at the simplest particle level could, you know, how do you think this is doing it? And it really gets them thinking, talking. There's a lot of conversation in the classroom.
Yeah.
But the thing that makes it modeling is that there is a goal to get something described that is a pattern that includes the structure of matter as well as its behavior. And it happens in chemistry. This approach was being explored that we found the most effective thing we could do was start from the simplest idea of matter and get more complex as we went, so that you'll notice we're just drawing little circles. But by the end of the school year, we've got Lewis dot structures and all this other stuff going on. We have all the stoichiometry. We have, you know, understanding the whole structure of the atom from protons, neutrons, electrons, energy levels. All of that is going to be part of the discussion, but we start simply so that every time the students make a change in what we understand, about matter itself. They have a foundation for knowing why that got introduced. It was necessary, not just what the teacher said we were going to learn next. So also, one of the things that's very distinctly different here is that you would have been in a workshop doing the experiments, creating the whiteboards, having the discussion, having your workshop leader interact with you like a teacher would, and then slowly over the course of the workshop, shifting gears until you were beginning to take that role of helping guide discussion on the X, something about an activity or a worksheet or a problem set, something where you start to learn how to carry out this dialogical approach to teaching. So the lab, the workshop is a place where we do try to give you the experience of the classroom experience first from student mode, and then to begin to figure out how do you frame questions to get students to understand something rather than just telling them. My first workshop leader, Don Yost, I will never forget, and it's been a very long time because it just struck me. He said, the hardest job I've ever had is trying to get into the heads of my students through conversation. So, and I don't know, I have found it to be absolutely satisfying. I've been doing this since '98 and I just retired this year. So the feedback of my students is so powerful and compelling to me. So any other questions?
If I may just add something here.
Sure.
I'm a retired physics teacher, and I was a modeler, in the physics field. And I can tell everyone that there is nothing that replaces the idea of attending a workshop. Only through that you really get the whole, concept of how this process works. It's incredible. It's a wonderful experience. So I cannot overemphasize the importance of doing that from a teacher point of view. You need to see how you would experience it as a student, and from that you will be better prepared in how to do the same approach with your students. So yeah, I second that, Brenda, big time. Thank you.
Thank you for that endorsement. Can we go just to non-sharing so that we can see each other? We're about to wrap up here. But yeah, it's like the difference between, we can show you here, but the difference between trying to learn to ride a bike by watching videos and having somebody describe it to you versus getting on the bike. And the workshop lets you get on the bike. So thank you so much for joining us. We want to honor your time. It is now the 90-minute mark where we said we would end. But if someone wants to hang on for a few minutes and ask some more questions or have a conversation about something, we would be very happy to do that. So
thank you for coming. Yes, thank you for your time.
All right. So thank you so much for coming.